Hey, how you doing? Thanks for joining me today. In this video, we want to take a look at different loads connected to the same three-phase power supply. In this example, we're going to use unity loads for simplicity. In the next video, we'll take a look at a load with a different power factor for analysis. If we take a look first, right here, we have our Y-connected unity load, and we have our delta-connected unity load right here. And we're going to look at how these compare to each other on the Cartesian plane, as well as we'll be able to see the differences between a Y and a delta load connected to the same power supply. So, first of all, we have a 120, 208 volt, three-phase supply here. We have our lines A, B, C, and we have our neutral in there as well. So let's take a look at our Y-connected load here first. So, from my A to neutral, I'm going to have a phase voltage. Well, let's look at the line voltage first. We have a voltage of the line is equal to, if I were to measure line to line, I would have 208 volts. And because we're connected to the same supply, we can say the same thing for our delta connected load as well. So we'll say voltage of the line here is also 208 volts. Now, when we look at our Y-connected load, our phase voltage is not 208 volts. It's going to be 208 divided by root 3. That's going to be our voltage of our phase, or our voltage A to N. I'm only going to look at the A phase here in this video. So voltage of the phase is 208 divided by root 3 is 120 volts because of that neutral point in there. Now, when we talk about our delta load, if we look at our phase, well, A to B is actually connected across line A and line B. So realistically, our phase voltage is the same as our line voltage. So voltage of the phase here, 208 volts. So we can already see, as mentioned in previous videos, that our phase voltage on our delta system is root 3 larger than it is in our Y system. Okay, so the next thing we want to take a look at is the currents. So first thing we're going to look at is the current in our phase. Let's give ourselves some impedance value on these phases. Let's keep it simple and we'll say 10 ohms. Okay. And we'll keep it the same with our delta as well. There we go. All right. So Ohm's law, if I want to find the phase current, I need the phase voltage divided by the phase impedance. In this case, 120 volts divided by 10 ohms of impedance should give me 12 amps of line current. And if we're focusing on the A phase right now, well, we'll get to that when we do our Cartesian plane. Okay, we'll get the angles down when we get there. If we look, if I have 12 amps coming in on my phase, well, there's no difference between that 12 amps on my phase and that 12 amps on my line. So we know in a Y-connected circuit that I line is equal to I phase. So what we can say is I line is also 12 amps. So there's our phase voltage, our line voltage, our phase current, and our line current on our Y system. We already have our line voltage and our phase voltage, which are the same on our delta. Let's figure out what our phase current and our line currents are. So again, same thing. The only difference is now I have 208 volts is my phase voltage on my delta system divided by the same 10 ohms of impedance. We end up with, let's cross that out. I phase is equal to 20.8 amps. That's my phase current. My I line for a delta system, we know one of the rules with delta, if it's a balanced system, my I line will be root 3 larger than my phase current. So I line equals I phase times root 3, which in this case 20.8 times root 3 should be about 36 amps. Okay, so again, as in previous videos, we see that our line current is about 3 times the size of our line current when we go from the same delta load to the same Y load. These are both on the same power supply. So we're going to take a look at the actual phasors in this circuit so that we can see the comparison. So, make ourselves Cartesian plane here. And the first thing I'm going to draw on here, because it's common to both of these, is the voltage A to B. We're going to use that as our reference. If I look here, if I took a meter and I went VA to B, I'm going to plot it. Well, let's use a different color. Right here. There's my VA to B. Okay? Down here, 120 degrees behind it, we should see VB to C. And up here, either 120 degrees behind VBC, or we can say 120 degrees ahead of A to B, we see VCA. There's our 3 line voltages. Now I say line voltages because in a Y system it is our line voltage. It's also our line voltage in a delta system, however it is also the phase voltage in a delta system. So that's why we want to use it as a reference. Now, with these Y-connected phases, I have a 120 volt. Okay, and one of the rules with our Y-connected system is that our phase voltage will lag our line voltage by 30 degrees. So we're going to draw that on here as well. Here's our 120 volt. I'm just going to call it VA to N. Okay, that's our 120 volts, A to N, lagging our line voltage VA to B by 30 degrees. Okay, so there's our voltages on there. Now, I'm going to plot our currents on here so that we can start to look at the angles. Okay, we're going to use, this is going to be our, we'll say this is our Y current. And let's go with, there's our delta current. Okay, so that we can see the difference between the two. All right, so first thing we said that our phase current in our Y system was 12 amps. Because this is a unity load, we know that that 12 amps is going to be in phase with the phase voltage. Okay, so we're going to plot that on here first. We're going to say right around here, there's our I, and we're going to call this A. Now, this is line current and phase current in a Y system, so I'm going to call it IA. I'm going to put a little Y right here in brackets, so we know that that is the line current for our Y system. Okay, because the next thing we're going to take a look at is our delta system. We have our I phase current of 20.8 amps is in phase with its phase voltage. Remember that line voltage and phase voltage are the same thing. So when we talk about phase voltage on delta, we're talking about A to B, which we plotted right here, which means phase current is in phase with this phasor. So we're going to plot that on here, 20.8. Oh, we'll switch to the purple because that's our delta current. There's our, we'll call this I, A to B, and we'll indicate that little delta symbol right there so we know we're dealing with a delta phasor. Now the last thing we need to plot on here is our I line for our delta circuit as well. One of the rules with a delta balanced circuit is that when we look at line current, it's going to lag the phase current by 30 degrees. Remember, when it's balanced. Okay? So that means if I look at IAB at 0 degrees or in phase with the phase voltage, it's going to lag by 30 degrees, which puts it on this same line right here. So let's plot it on there. 36 amps should be about 3 times the length of this one. 1, 2, right about there. There we see our I line A for our delta system. Okay? Now, what we want to find is right here. We want to know, what is the current at that point X? What is the combination of both of these line A currents to both of these loads? Because they're at the same angle, they're both at 330 degrees, we can say this is at 330 and this is at 330. I can add those together without the use of an HV chart because it's just straight addition at this point. I have IA is equal to IA from our Y plus IA from our delta. If I substitute these for numbers, we have 12 amps plus 36 amps. I end up with a total of 48 amps on line A. Okay, and it works out at 330 degrees as well. You could do this same method for all three of your phases of your volts B to C, your volts C to A. You could do the same thing with your currents and your phase voltage for your Y as well. Hopefully this has helped. As I said, in the next video we'll take a look at different loads from the same three-phase supply with a power factor in them as well. Thank you for watching. We'll see you next time.